Welcome. We are looking at the definition of scalars and vectors, and we are trying to see how this notion can be generalized. Scalars are quantities which are just represented by magnitudes, they are just numbers. Vectors are quantities which have magnitudes and directions. So, this is the traditional definition, which is correct of course, but it has the and it is also very straightforward, easy to understand, but it makes it very difficult to define what a second rank tensor is, because it is difficult to explain in kind of these kind of terms as to what a second rank tensor is. So, it is possible to generalize, and for doing that the first thing we do is to define the components of a vector. So, we now consider that vector is a quantity with magnitude and direction, and you can represent this information of its magnitude and direction by resolving it along the coordinate axis. So, we define an axis, a system of axis, a coordinate frame of reference, and we take this vector, we resolve it along each one of those directions, and we give the components, and that can now be represented either in a matrix form as a column vector or in a symbolic form by giving an index. So, now we can define scalars as quantities with no indices, vectors as quantities with one index, then that naturally generalizes to second rank tensors are quantities with two indices, third rank tensors are quantities with three indices, and so on. So, you can define an nth rank tensor which has n indices, for example. Now, this also is problematic because we know that vectors exist without reference to any reference frame, right. Frame of reference is our way of describing a vector. So, we do not want our description to change the way we look at any vector, or we want to demand that different ways of representing the vector using different frames of reference, they should be consistent with each other. This is possible only because the vectors have their own existence. So, they do not change, and that helps us define vectors in yet another way, which again is very favorable for generalization. That says that take the vector, take your first frame of reference and resolve it along the directions, and it has some components. Now, consider the new frame of reference, take the same vector and find the components along the new coordinates and take this quantity. See if these two are related through what is known as a transformation matrix. So, we define the transformation matrix. So, I am going to redo it once more just to make clear. So, you have a old frame of reference which is defined as x1, x2, x3. So, we are going to mostly deal with a 3-dimensional space and Cartesian vectors, and there is a new frame of reference which is defined as x1 prime, x2 prime and x3 prime. The direction cosine a11, for example, a11 is nothing but the direction cosine of x1 prime with x1, right. And so, first one represents this primed quantity, and the second one represents the unprimed or old quantity. So, in a similar fashion we define a12, a13, a21, a22, a23, a31, a32, a33. This we call as a transformation matrix. And now, if you have a vector j which is represented in the new frame of reference, let us say that its components are j I prime, then you know the components of this vector in the old frame of reference. I think yesterday I made a mistake here, it should be j j. These are the components in the old frame of reference, these are the components in the new frame of reference. If they are connected through this relationship, a I j j j is j I prime, then if that is the condition we say, then we say j is a vector. Remember, this is possible only because J has its own existence. So, we take two different frames of reference, we take the same J, we find out its components in these two frames of reference, and once we know the two frames of reference, we also know how they are connected through this transformation matrix. So, we see if the components we get by resolving in the new frame of reference the same vector, they happen to have this relationship with the components from the old frame of reference. If it says, then we call J as a vector. Okay. So, this definition automatically helps us generalize to higher order tensors also. We will see an example, especially with respect to the diffusivity and flux and concentration gradient scenario, that is taking the Fick's first law, we will try to understand. But while doing that, it is also important because we said that the diffusivity, which is a second rank tensor, right. We said that Dij is nothing but a second rank tensor called diffusivity, and this also had a matrix representation, which was like D11, D12, D13, D21, D22, D23, and D31, D32, D33. Now, if you look at, so this is also a matrix, but this is representation of a tensor, and the transformation matrix, the A, is also a matrix. It also has this same structure, but these two are completely different entities. This is a property, okay. Diffusivity is a property. So, the D is a property tensor, okay. There are also tensors which are not property tensors, we will discuss them. By now you might have guessed, for example, flux is a tensor, is a first rank tensor, but that is not a property. Concentration gradient is a first rank tensor, but that is not a property, okay. But diffusivity is a property, right. So, a tensor which represents a property is a property tensor. Because this is a property tensor, this exists on its own, okay. Now, when we are referring to some particular frame of reference, we might be able to write this diffusivity in this matrix form, but the existence of D is independent of whether we are able to represent it in this form or some other form. On the other hand, the transformation matrix A necessarily depends on having two different frames of reference. The way to think about it is that I have a frame of reference that is x1 prime, x2 prime, x3 prime, and I have another frame of reference x1, x2, x3. A is a quantity which is like the bridge between the two. Now, if you remove this, A does not have any existence. If you remove this, A does not have any existence. Okay. If you do not have any frame of reference, A does not have any existence. A is something that straddles one frame of reference and another frame of reference. Its existence is completely dependent on first being able to define two different frames of reference. Only when they are defined, you can define A. On the other hand, D is a property tensor that is completely defined for a given particular system. Now, whether it becomes this or some D11 prime, D12 prime, D21 prime, etc., depends on the frame of reference that you choose. Even then, for example, I might have only this frame of reference, D is completely defined in that frame of reference, or I might have only this frame of reference and D is completely defined in that frame of reference. When you have these two, then you have two D's defined and they are related to each other through a relationship, which is what this A is all about. So, we need to think of A as some quantity which connects two frames of reference. So, it acts like a bridge or an entity which talks to these two frames of reference and make sure that things that you define in one place can be translated into things that you define in the other place, but it does not have an existence of its own. On the other hand, property tensors have an existence of their own, and that existence is independent of your even defining a frame of reference. So, this is a very important distinction that we need to make. Transformation matrices are different from property tensors. Transformation matrices are matrices, irrespective of whether you are defining second rank tensor, third rank tensor, fourth rank tensor, they are just matrices which have this form in 3 dimensions, they are 3 by 3 matrices. On the other hand, if you have a third rank tensor, for example, it does not have a matrix representation in the same way as a second rank tensor has. So, second rank tensors have a matrix representation which in 3 dimensions looks similar to that of a transformation matrix, but these two are very different types of entities. They just happen to have a matrix representation in both the cases. Okay. So, it is very important not to confuse between a property tensor which is represented as a 3 by 3 matrix and a transformation matrix which is used to define the relationship between two different frames of reference, which is also defined as a 3 by 3 matrix. Okay. So, now that we have done it, let us try to see how to generalize the notion of a vector to a second rank tensor. Okay. What is our new definition? Our new definition says that a vector is a quantity which transforms under a coordinate transformation according to a given set of rule. What did that rule say? Suppose if you had j I prime as the representation of the j vector in the primed frame of reference, it is related to the unprimed components of the same vector j through the transformation matrix Aij. So, anything that obeys this would be called as a vector. Now, if that is so, what is a second rank tensor in terms of Aij's? Can we define what is a second rank tensor in terms of the transformation matrix? The answer is yes, we can do, and that is what we are going to do. Okay. So, we know that in the regular frame of reference J I is nothing but minus d I j del j c. So, now we are going to replace for the j j. Please remember, I mean this dummy index thing you have to keep in mind. So, you can't, because this is j I, you can't put d I j here, because this I then will get summed over according to Einstein's summation convention. Whereas, in this equation I is to be a free index, because in the left hand side I is a free index. So, that has to be retained. So, this is where you have to use some other dummy index when you replace for j. Let us do it. Okay. Aij, jj is nothing but, so minus d j k del k c, right. D j k del k c is nothing but j j, right. This will get summed over and that is j j, and j j with a I j will give you j I, right. So this is, so we are looking at this quantity j I prime, which is a I j j j, and j j is getting replaced by this quantity. And if j I prime is a I j j j, you can also represent by the same token j I in terms of okay. So, like the components in the new frame of reference are related to components in the old frame of reference through Aij, you can also relate the components in the old frame of reference to the components in the new frame of reference using this. So, now del k c I am going to use this kind of relationship, right. So, I am going to say that del k c in terms of new frame of reference is going to be, so it should connect to del k c prime, it cannot be k because k is going to come here in a k. So, I am going to say a l k del l c, okay. L and L will get summed over, k is what will be left. So, I am going to replace this d k by minus a I j d j k a l K del L C prime, right, that is the prime quantity. Now, you can see what is it that I have got, J I prime, let us say, is equal to D I J prime del J C prime, right. If I have to write it like this, then I can see that this quantity, okay. Now, I need to be careful, it is yeah. So, these are dummy indices, you can write it in whichever way you want, but K is summed over, L is summed over. So, L is the free index that is left and J is summed over. So, it is I L del L, right. Remember, this is a dummy index, it could be any, it does not matter. So, what does this say? This says that D I J I L prime, for example, is nothing but minus A I J D J K A K L, right. J J will be summed over, K K will be summed over. So, you will have I L left. So, you now define second rank tensors as quantities. No, this minus sign is not there, right. So, this is because J is minus this. So, minus is absorbed. So, D I L is nothing but this quantity. So, now our definition, so generalized definition, we are going to say that scalars are quantities which do not change under a coordinate change. Now, vectors, let us say like J prime, or quantities which change like this. Second rank tensors like D I J prime are quantities which change like this, D I J, I have to say D K L, for example, A I K A J L, right. L L will get summed over, K K will get summed over, I J will be left behind. So, second rank tensors are quantities which transform when you do a coordinate frame change in such a way that you have to take the old components and you have to multiply by the transformation matrix twice. Similarly, I am going to define a third rank tensor, let us say some epsilon I J K as one which transforms according to the following rule, A I, so this is prime epsilon L M N A I L A J M A K N, right. So, depending on how many times you multiply by the transformation matrix, if you multiply by 0 times, that is the scalar. If you multiply by 1 time, that is a vector. If you multiply by 2 times, that is a second rank tensor. If you multiply by 3 times, that is a third rank tensor. Now, I can define a fourth rank tensor, I J K L is equal to A C P Q R S. So, it is L S K R J Q I P, right. So, P Q R S will get summed, I J K L will come. So, this now defines a fourth rank tensor and so on. Okay. So, this is the third definition that we have for vectors, which is again generalizable. So, first definition said that vectors are quantities which have magnitudes and direction. Same information, but was put in a different language when we said that vectors are quantities with a single index, when you refer to a specific frame of reference. Now, we are defining vectors as quantities which have its components transform in a particular fashion when a coordinate transformation is done. Both this index definition and this coordinate frame change definition help us generalize to higher order tensors. Okay. So, we have now shown that for example, second rank tensors transform according to this law. So, we go back and then we make it a definition. If this, then D is a second rank tensor, okay, and so on. So, for everything now we can have a definition which is based on these coordinate changes, right, transformation matrices. Okay. So, so this is how we generalize the notion of a vector to a first rank tensor, so that it can then help us define higher order tensors. Okay. So, we have defined it in two different ways. One definition says that the rank of a tensor is defined by the number of indices that is required to represent that quantity in any given frame of reference, and the second one says that under a coordinate transformation, these quantities transform in a particular fashion. If they transform like that, then we call them as tensors, and that also helps us generalize to higher order tensors. Okay. So, the next step is to see what these transformations mean, or if there is a way we can understand the second rank tensors a little bit more better. That is what we will do in the next part of this lecture. Thank you.